So again, like I've been mentioning for weeks, this week in particular, today's end of Q1, grades are due at 2:30, right? So if you still got missing stuff, right, if you want to resubmit parts of your project, which I highly recommend if you're missing some stuff, get stuff in for that project. That needs to happen by 2:30 today. End of the school day, your grade is stuck at whatever it is for Q1. And then every grade after that is going to be shifted to beyond Q2 towards your semester grade. Your semester grade is an average of your Q1 and Q2 grade. Just in case you didn't know, that's how it worked. I had a virtual student come in who had a very low grade, finished their project, submitted their project to me, and their grade went up 60%. Not even kidding you. Like 60% increase because of one assignment. I was telling you guys, projects are a big deal, not only for this class, but also it's reflected in the grading, right? A project grade has way more impact on your grade than just a homework or an in-class assignment grade. So, if you have a choice between doing like one or two missing assignments or getting this project wrapped up, pick the project. It will boost your grade much more. Don't waste your time, because again, we're down to the wire. Right? Hopefully you guys have been on track all year long and you don't even have to listen to me really, because it's not an issue. But if you are missing stuff, you're missing stuff for your project in particular today, by the end of the school day. I've tried to remind you over and over, like weeks in advance to let you know, but now it's down to the wire. Drew, do you have a question? Okay, maybe wait. So ask me when we have some work time. Just call me over and I'll get you what you need. So that's that. Connor, I think I got your. Oh yeah, from last time. Again, any questions on that? When we have work time, let me know. I can try and help you the best I can. So today, what I want to do, we are going to finish up assignment 211. What were we talking about last class? What was this new topic that we were... Yeah, that's the overall unit. Good. So we're now in this unit where we're working towards making assemblies, putting parts together to make things. Yeah, tolerances. That's what we're focusing on now. One, I need you guys, I'm reminding you, phone should be away. Right? We don't need them. Keep them away. I don't want to have to send it to the office and let it sit there all day. Right? Tolerances. Tolerances are basically a margin of error that you give on your part. Engineers cannot expect that if you design a part to be 1 inch long, that it will be 1 inch long. That's not how the world works. Huh?
Not everything is exact.
Yes. You will never get exactly 1 inch. So what you have to do as the engineers realize, like, the machines we use to make stuff have limitations. I need to account for that in my design. That's where you give a tolerance, right? We talked about toy blocks. You build blocks for kids to play with and build stuff. Do you need a high tolerance?
Yes.
No, you don't, right? You could say the block is 1 inch plus or minus, 1/4 of an inch, right? I don't really care all that much. So why would I make, my company manufacture this so precisely? It's a waste of money. It's expensive to make parts precisely. You need high-tech machines if you want high precision. Now, if you're making, again, the classic example is components for an engine. You better bet you're going to have a very tight tolerance, right, within potentially the 1,000th of an inch. The reason is you need that part to work. You can't afford to have a failure happen, especially on something like an aircraft. If your part fails in the engine and your engine fails, you're now putting people's lives at risk. So that's when you can justify having, say, a tolerance of 1/1000th of an inch, where you can only be off by 1/1000th of an inch. If you're off by more than that, it's not acceptable. You can justify that because people's safety is at risk, right? Now, certain parts of the aircraft, right, like, I don't know what they call it on an aircraft, but the steering column, right, the grips on it, I don't need those to 1/1000th of an inch. It's not important to the function of my design. It's just kind of aesthetic. So that one, I'm going to loosen up my tolerance and give you like 0.2 inches, right? It just needs to fit on the metal bar, right? So that's what you need to be thinking through when you design stuff is, what tolerance do I need? You need to have as much tolerance as you can. You want an accurate part, but you need to be within reason. You need to come down as much as you can to cut costs. So that's kind of the balancing act that you play when you list tolerances on your part. What we did is we took... I don't know where I put those. Oh, yeah. Remember last class we took these blocks and I had drilled holes in them, right? My design was whatever size the drill bit was. Did we find that that's exactly what size the holes were? No. It's a prime example. I designed it to be, 1/4 inch. It was not. That's how the world works. Your drill bit, it'll say 1/4, it's not actually. So I need to figure out the tolerance, right? The next thing that we're doing, the continuation of 211 and talking about tolerances is something where what happens if you put two tolerances together, right? Owen was saying this unit is all about assemblies. We're putting parts together. What happens if I have a hole and a pin, right? Let's say I have a dowel. This is a steel dowel, steel pin. What happens if I have to put these parts together? This has a tolerance.
It's going to be loose.
Yeah, it depends, right? If my tolerance is 1/4 inch plus or minus 1/100th of an inch, and my hole is 1/4 inch plus or minus 100 or 1/10th of an inch. No, 100. Yeah, if both parts happen to be exactly 1/4 inch, they will just barely fit together. And these do, right? They're nice and snug, so I know they're exactly the same size. What happens if my hole was on the low end of the tolerance? So it wasn't 1/4 inch, it was 1/100th of an inch less. Yeah, it wouldn't fit. Especially if my rod was on the high end of tolerance, 1/4 inch plus my tolerance of 100. It wouldn't even fit. My rod is bigger than 1/4 inch. My hole is smaller. It definitely won't fit. That's what this one would represent. They do not fit. Yeah, but then you'd create a new hole, basically. So that's the problem as an engineer. If I give those tolerances, that's a bad decision. Because my part could be big and small, and then it doesn't work. Well, that defeats the whole purpose of making the parts. So that's what we need to be thinking about is the tolerances on two parts need to agree with each other. This is where I'm gonna introduce the second part of this activity. And it's fit. It's a self-explanatory phrase. Fit is how parts fit together. The problem is I have tolerances on both parts. Hayden, Jesse, Drew. Hayden, have you wake up, please? So when you fit two parts together, they have tolerances. Depending on what kind of parts they are, you need to make sure that you account for the tolerance that you give. Because like I said, in some cases, you make a bad decision and it won't work. Why is that up? Must have had an update. Huh. There. So what I'm going to do is I'm going to go to 211, and I want to remind you the three types of tolerance that we have. Remember these? First type, unilateral. I tell you, this is what I want my dimension to be, and you have room for error in one direction. That's it. This part, you can go a little bit bigger than my specification, but you cannot go any smaller. That's unilateral. Can I have that, please? So unilateral is you only get a tolerance, you only get room for error in one direction. That's it. Bilateral is bi is two, right? Bicycle. I have tolerance. I got room for error two directions. I give you my part. You can go above or below by a certain amount. Third type is a limit. I tell you, between here and here, as long as that's satisfied, we're good. Right? You don't actually list the design specification. You just say somewhere in here, I'm happy. So if we have those three types of tolerances, what you then have to look at is how those tolerances fit together. There's three types of fit. Fit is when you put two parts together, how do they fit together? It's a self-explanatory title. A clearance fit. Right? Have you ever been through like a McDonald's drive-thru or something? They got that big like yellow bar. Say like clearance 13 feet. That means the gap that you can fit through is 13 feet. It's the space between two things. In a clearance fit, clearance means there's room between your two parts. If I take my 1/4 inch dowel and put it in a 5/16 hole, there's a gap. That's called clearance. There's clearance between my part and the hole. That's a clearance fit, right? It's basically a loose fit. That's a very simple way to think about it. Limits the size of mating parts so that a clearance or space gap exists between the two parts. A loose fit. Now on the other end, interference fit means there's like friction or rubbing. So technically when I put 1/4 inch into a 1/4 inch, this one happened to be almost exact. You see how there's friction it's holding together? This does not hold together. That's because there's a clearance or a gap. An interference fit is there's interference between the two parts. They interact. Right? Two parts which is achieved by friction after they're pushed together. So if you have to push two parts to get them to fit together, that's an interference fit. Right? You have friction, there's rubbing between the two surfaces. The other type is a hybrid of these two. It's called a transition fit. Two parts can sometimes have clearance, sometimes have interference. Right? If I get my hole and my rod to be exactly the same diameter, same size, I have interference. They fit snug, they have friction. What happens if I'm on the low end of the tolerance for my rod? I'm less than a 1/4 inch. Then I'm going to have a clearance fit. Because this is smaller than the hole. It'll slide through easy. It doesn't rub. It doesn't have friction. Transition fit is where it could have either or. Right? It's on the tipping point. It could go one way or the other. Does that make sense? The other thing you might be thinking of is what happens if they don't fit together, right? If this is too big that they don't even go in together, well, that's a non-existent fit. We don't bother to name it because it doesn't fit. So, right, that's the other extreme that we can be looking at. So if I look here, this is my example, right? I have like this pin and a hole. The hole is between 9.9 and 9.85. My pin is between 10 and 9.92. Right? So technically, in some cases, this might not work. Right? Brody was talking about, well, just ram it through so that you force it to fit. In this situation, that's what you would have to do. There will always be material interference, right? The smallest pin is 9.92. Well, the largest hole would be 9.90, right? So if I jam that pin in there, I'm pressing on that hole and making it bigger and forcing it to fit. That's why it gets stuck in there. So Brody was talking about that. That's what you do here. This is an interference fit. It's close enough that you can press it in. This would be a transition fit, right? If I have my hole or my pin at like 10.13 within my tolerance, and this is maximum 10.12, that'll barely fit. I'm going to have to press it in, but then I get interference. There's friction. It fits, but it's snug. That would work. I could also have my hole be at the low end of my tolerance, 10.08, small. As small as I'm allowed. My hole could be as big as I'm allowed at 10.12. What kind of fit would that be? If my pin is 10.08 and my hole is 10.12. Clearance fit. The hole is bigger than the pin. I have a clearance or a gap. So depending on how this part is manufactured, right? It could be anywhere in here, anywhere in here. These tolerances produce a transition fit where it could be an interference or it could be a clearance fit. That would be something you would have to think about as an engineer, right? So if you want to have a rod and a hole that connects the blocks without allowing motion, right? I'm going to have two blocks, and I want to connect them together. What type of fit would I want if I want to prevent motion between the blocks? Do I want interference fit, a clearance fit, or transition? Yeah, I'd want interference. I want them to fit really snug and tight so that they don't really move. Right? What happens if I want free motion or rotation but not being able to move it in the hole? Drew? Clearance. If I have a clearance fit, I can rotate it, but I can't move it side to side. At least not enough that's reasonable. Right? It's going to stay together, but I can rotate it. Depending on what I want as the engineer, changes how I tolerance stuff. To store the tolerance block on a pegboard. This one, I don't think it matters. Right? If I have this on a block and I want to store it, it doesn't matter, does it? I don't care if it's a interference fit like this, or if I can just drop it on there. Yeah, I'm just storing it. I don't really care. You would have to know that as the engineer, like, I don't really care. I'm going to give a big tolerance window. It could be interference or, right? That's when you do a transition fit. Because you want either or. All right? What questions do you have about fit? Does it make sense? Again, we're looking at tolerances. There's different types. We're now looking at, okay, how do we put tolerances together? What's happening? That's fit, right? We're getting on this idea of putting parts together. So, what I'm going to have you do is I got a practice sheet that needs to, this I'm going to collect before you leave, right? The first three are just general examples of tolerances. You're going to see there's three apart and a table with 3 entries on the first one. You're going to need to identify, hey, where are the tolerances in this part drawing? Label them A, B, C, whatever you want. And then in the table, you're going to write A, whatever tolerance you pick, and you need to fill in this chart. You need to tell me what type of tolerance is it? Unilateral, bilateral, or limit. You need the written explanation part. Basically, give me an inequality, right? The dimension needs to be less than this, but greater than this. Just write an inequality for that written explanation. The tolerance. If I ask you what the tolerance is, do you remember how we find the total tolerance? You got plus or minus 0.2 inches. What's the total tolerance? 0.04. The total tolerance is the total window of error that you could have. And then the y, I don't want you to do that. Just cross out the y column on every, all 3 examples. Then on the very back, it's got some questions about fit. Looking at how do you get tolerances to fit together? How would you design them? How would you consider them? Last class? Yeah. No, because that was Monday. No, I don't think we did. We had, I think, a really light day. All we did was talk about tolerances, didn't we? And then I gave you guys work time. Is that correct?
Yes, I don't remember.
Oh, yeah, we measured. So, no, there was nothing you need to turn in. Yeah. Again, it's been a long week for me, too. So. Yes, this worksheet, I need you guys to finish and turn in to me before you walk out. Again, you have plenty of time. Like, an hour? Jeez, you guys get through stuff a lot faster than my other class. Yes, you guys do listen. That makes a big difference.
I'm like 2 tired classes.
Yes. I will be walking around. Any questions you have, please ask me questions. It's new material, right? I want to help you understand this. If you get stuck, raise your hand. If you have questions about project stuff that's due today, let me know. But I'm going to just walk around helping you guys get this sorted out. And hopefully at the end of this we have a grasp on tolerances, what they are, and then we have an understanding of, or start to understand, how do I put tolerances together? How do I consider what tolerance I should give to 2 parts so that they fit together and work correctly? Luke? Did you label? A, you need, where is a tolerance? Right, these are just dimensions. Where's a tolerance listed? That's one, right? That gives you, hey, here's a limit. This dimension could be between here and here. So there's this, what I would label as A. And then you would describe that. And then you need to borrow writing pencil. Oh yeah, they're right up here. Take a pick. Right? And this would be, say, B, that's C. That doesn't matter. But then up here, right, you describe A to me. What type is it? What's the rate, right? Inequality. What's the total tolerance?
So like, we're using all three of the tolerance tests right here.
Yeah, there's 3 of them. That's why there's 3 lines. You gotta, no. You just identify it. You don't necessarily use unilateral, bilateral, or limit. These are all limit. You gotta write down limit. Other ones could be different. What's up?
So for the tolerance type, considering these are all limit, do you just want me to put limit
Yes,
here?
yes.
Oh,
It's literally, you said this is A. What is A? It's a
Okay.
limit. What's an expression? Well, just say like X is between this and this. Just give me an inequality, and then give me the total tolerance, which is just the upper limit minus the lower limit. Right? The total range of error. That makes sense?
Yeah.
And then there's 2 other examples.
That's going to be the most
Correct. Not Q1. But your test today will not be quarter 1. Basically, I can't grade it.
So what you're telling me is like,
It's yes. Some teachers
okay,
like
so
they have a turnaround time on their like I cannot grade your test within 6 hours because I'm teaching. So that's why the test technically it's counted on quarter 1 right now because quarter 1 ends at the end of the day. But for graded purposes, like I can't make it forward. So they push back. Some teachers say like whatever week the quarters change, that's week 2. And it gives them time to grade stuff from like last Friday so that it's in by 2. So I'm sorry if that's confusing. No, yeah, don't worry about it. Whatever your grade is, that's what it is. This test, I'll want to tell you. Yeah, Spaceman rings a bell. Yeah, I would have to look it up. I don't know if that's like a scholarship program or nice. Yeah.
so A.
I didn't do that. I vaguely heard of it. You'd have to look it up and research it. Anything. You need to find the tolerances on this part and label like, oh, here's one, I'm going to call that A. And then describe A. And I'm going to say, oh, here's another one, I'm going to call that one B. And I'm going to describe B. Yeah. So you're looking for 4 tolerances. Good. This is the type, like, is it limit, unilateral, or bilateral? And then this is just what this is the total tolerance. Remember, like the total tolerance in between both sides. Yes, if it's plus or minus 0.2, then it's 0.4. Correct. It's the total like range of error you can have. Okay, good. That's yes. It's a 50-50. It's like do I cross out Y on all of them? Correct. Yeah, you label them. You gotta find the 3 of them. It's the same. A, B, and C. You just need whatever you want, and then your A.
Hello.
You call it A. You describe
Hey, Carly. That was a nice phone drop you did during the.
You went down.
Let's see what's up.
You went disappear.
Like
Maybe.
Just on you label whatever you want, and then whatever the corresponding spot is, you describe. I know. C.
I know I don't mean a magic trick.
Yep. Remember we talked about that last class, and I reviewed it here. There's unilateral, bilateral, or limit. You have error in only one direction, not the other. That's unilateral. If you get room for error in 2 directions, that's bilateral. And if it says, hey, as long as it's between this number and this number, that's a limit.
So if I have
on the front page, all of those tolerances that you find, they're all limit tolerances. Because they give you, for this part, I want it between the 2 numbers. That's the limit.
alright, so when there's 2,
Yeah, it'll give you two numbers for the measurement. What it's telling you is somewhere between, right? It gives you the limit. Everything else would be like this measurement plus or minus, right? That one, what I really like the best simplest way is to give me a compound
We're not
inequality.
doing the wise.
Yes, just say like x has to be between this number and this number. If it's a limit, that one's easy. You know the two numbers that need to be. But if it's a like bilateral tolerance, you got to take the measurement at the tolerance. That's your upper limit. Subtract the limit. That's your lower limit. So yeah, x is between.
Would we do these?
Your arrows are not facing the same direction.
Oh yeah.
It's weird. You take two inequalities and smash them together. Right? So this says x has to be less than this. Is that your upper limit?
Confusion.
And then x has to be greater than your lower limit.
We don't have to do the lot.
Correct. You guys cross out the column that says y. Cross that out. I don't want you to worry about that. The y column. It says the word y.
Oh.
Yeah, not the letter.
Okay. Brody, what's up?
Alright? Show me where's the tolerance listed on the part. Right? This is not that's a dimension. That's not a tolerance. Where's the tolerance?
Same rate.
Nope, that's just says the diameter. This is a tolerance. So you need to say, like, label this A. This is the same part. This is a multi-view drawing. Right? These only have one view, but this is a multi-view.
Oh, that makes more sense.
Yes. Yes, sorry.
I thought they were completely different.
Yeah, if you flipped over, you would like see like, okay, here's number 2, here's number 3. Yes. Sorry if that was confusing. Yeah. So then you find it and say, okay, here's one, I'll call it A. Another is B, another is C. And then describe ABC. Yep. The top. Yes, this is good. But your explanation, give me a number. Right? This one is if they're looking say X. This dimension needs to be put it in the middle. Have you written like compound inequalities before? Put X in the middle. And on the left have an arrow, the right. You know what I'm talking about? Okay. Think of it. So your arrows have to go in the same direction.
Okay, nothing below.
And I'll show you why.
You're half the next place when you make it.
Yeah. So for this, you have to be the way you write this is upper limit. The upper limit is 0.5. Yes. Right? And if you read the inequality, x has to be greater than this. Well, that's true. It's going to be more than my lower limit, but it has to be less than my upper limit. That makes sense? The limits are easy. You have to something like this. You got to write, okay, the lower limit is this minus that. No. Yes.
Yeah.
My explanation, my lower limit is 0.5 minus here, that's 0.5. But my upper limit is 0.5 plus this. So those are my limits.
So basically writing the same thing.
Yes.
But different numbers.
Different numbers, yep, because they're different dimensions.
Luke?
Yeah, give me one moment.
Alright, so, for this, where's the measurement?
Where are tolerances listed? There's no tolerance on this dimension. That's not it. That's not it. What about that one?
Yes.
Yeah. It gives me a dimension plus, that's the tolerance right there. That's a tolerance right there. This is a tolerance. That's a limit dimension. Right? There's not one number, it gives you two. Well, those two numbers are the upper and lower limit. Here's another.
So,
Those are your four. Label them A, B, C, whatever you want. And then wherever you write A, you got to describe A. Just like you did before. We got that as B. What type of tolerance? Yeah. If you go to what we did last class, 2.1, I pulled up the reference page and it shows up there. It's just a summary of the page.
I just did that first. So then those two, okay, you know what? Yeah, I feel
That is mine. It's already the resource page.
I'm gonna keep it.
If you scroll down, right? Yeah, right there. These are the three classes right here. Limit, unilateral, and bilateral. Does that make sense? I know you were gone all week. Right? The unilateral is going to be like plus or minus. Like, this is unilateral. This guy, that's your unilateral. Because I only give every air in one direction. That's unilateral, right? Unicycle one. The other option, bilateral, is I can do air above or below two directions. Bilateral, bicycle. And then, like you saw on the front page, they give you two dimensions for one dimension. That's a limit. Right? I'm giving the limits that you need to be within. So those are the three types. Correct, right? You can put upper and lower limits for that measure. Yeah, it's a little weird.
Or where is it?
Neither. Right? That single measurement has two numbers. Well, what they're doing is they're doing a limit. They're saying, hey, the limit of this dimension needs to be within 2 and 2.00. Yeah. Where's your A? You gotta lay it around. Blue. So you gotta lay it around. And that's
No.
you gotta
No.
I only give you air in one direction. This is bilateral. Yeah, you can say one stop to the or minus. It doesn't matter. But both of these, they're limited. The limit tolerance. Right? They just give you something lower limit.
Seen it before.
Nobody here is tolerance.
Yes.
Done that on that.
Right? Tolerance.
I don't want you guys to
Yes. Yes. That's the total value of error that you tolerance, the total, right? If I say I can go 0.002 above and 0.002 below, what's my total window? Yes. Tolerance is the total range of error that I can have. Okay.
No, you're supposed to say hi back.
Yes. Yes.
That's every computer on 7. Yeah, before 2007.
I use them with them. Some just.
Every computer.
Hello.
Yeah. I didn't
Okay, so.
I don't want to do it. It's usually again, if you
So
were
there's tolerances.
but
This would definitely be.
yeah, at the end of class, to remind me all of this.
I'm sure it.
What about
They're basically tolerances that determine.
yes, okay, yes. That is,
Dimensions, unilateral, and
yeah,
bilateral.
it says there's 4 of them.
Smurfs getting mad. Blue. Smurfs getting mad. Yes.
Right?
No.
Are you on the fifth side now?
Yeah.
This one's really weird. And again, I didn't talk about that.
Oh, yeah.
No. This is the rod. So you're like, there's no tolerance given. The trick is, on engineering drawings, you see in the bottom left,
Most engineering drawings will give a general tolerance. They say everything is a tolerance of, and I apologize, the picture is really bad. It's 0.03. So it says, unless specified, all tolerances are this general tolerance. So that's how you know, like, well, if there's nothing listed, my general tolerance is just 0.03. Yes, because right, you have no tolerance in the negative direction, but 0.05. Well, the total tolerance is 0.05. So that is right. And I'm sorry that this one is obscure. That was, yeah. I'll share that with the class.
Since the given dimension would be none, right?
Not quite. I'll explain why. So you guys, can I get your attention, please? If you've gotten to the back page, right? This number 2, it says a bunch of questions. That is talking about fit now. We have this rod, and we're kind of put it in the smallest hole of the rocker arm on the very first page. So you need to consider the tolerances of both. There's a tricky question. Question B is, what's the tolerance of the rod length? And you're like, well, it just says it's 3 inches. There is no tolerance. However, what I forgot to point out is, if you go to the front page, engineering drawing, in the bottom left, there's this little note that says, unless specified, all parts have a tolerance of blank. It's called a general tolerance. They don't want to have to write that for every single dimension. So they just say, hey, everything has a tolerance of this general value, unless I specifically say otherwise. So that's when you see, like, okay, I need to go with my general tolerance. Again, I apologize that this is not very clear. The general tolerance is 0.03. So for B, it asks, what's the tolerance of the rod length?
Is that limit?
It's a bilateral.
Okay, so it's 0.06.
I suppose. Yes. You could write 0.06, or you could tell me plus minus 0.03.
Okay.
Those are saying the same thing. Good question. Does that make sense? Yes. I forgot to mention that. It's really misleading because there isn't a part drawing for that. So I just want to remind you that there's something called a general tolerance. Right? So that should help that number 2, that back page. So again, if you were done, just ask me, hey, we're finished, can we get on? Right? There's MacBook, other homeworks, give me something, and then I'll turn you guys down. No, they're working. Like, I got your guys' tests, and I'm like, I can't finish them, so I'm going to grade them later. Put them on Q2. But your projects, all weekend I was scrambling to make sure those were in and done and up to date. Today I got people submitting late stuff, so I'm like scrambling because those are on Q1.
Yeah.
That student that I told you about that jumped 60%, they went from 3% to I think 60. The room. Yeah. Well, they're not going to fail because he did the project, which is absurd. I don't know how that works. All right, I'll go ahead and end this. Again, virtual students, this document I'll put as a Word document, right? I'll post this to Classroom. You can type it in, right? You can fill this in electronically. Insert a text box to label like A, B, C, D as best you can, but then fill in the table, and then just type in your answers to the question for number 2, and then submit that to me on Classroom. So I'll make that assignment in a bit.